So welcome again. It's great to have everyone here for another experiment share. As you guys know, I'm Michael Gregory in Paris, France. Please feel free to all say hi, especially in the chat, as we're welcome everyone in getting started. It's quite a full lineup. I'm glad to see everyone who's here to share more experiments today. Takis, I think you're the first one on the lineup who's actually here. Are you okay starting things off today?
Yes, I think yes.
Okay, perfect. So then we'll turn over to Takis in Greece. It's great to have you back, and I'm looking forward to seeing the razor experiment or the resonance experiment. Well, you'll explain what it is, but unfortunately we had to. I forget why it was you weren't able to present last time. Probably my fault for changing the date. But sorry about the delay, and it's good to have you back again.
No, it's not your fault, Michael. I couldn't participate this day. It's because of my schedule.
Okay, so once it wasn't for me changing the dates around, because I feel bad when I need to change them. I change most of the dates.
No, okay, that's bad. I changed camera. Okay. I hope that it's okay. Nice. So I will try to be quite fast. First of all, hi everyone. I'm glad to be back. Here we have an electric machine for for the hair and for beard. I have removed the mechanism with the razors, and I have attached a string here. So when I push the button, that vibrates. It vibrates. Perhaps the vibration is not easily observed, even if I put it so close to the camera. But I suppose you listen, you hear the mechanism working. So the idea is that we ask our students to hold the other edge of the string. They can use whatever length they like, and try to produce a standing wave. What it is interesting, I hope, is the fact that the speed of the wave is proportional to the square root of the tension. They are not proportional to the square to the tension, but to the square root. So if we increase the tension by pulling harder, we increase the speed, so we increase the wavelength of the standing wave, and so we can have more or less nodes here. The bigger the wavelength, the fewer the nodes we are going to have, and it's very sensitive. I mean, with very slight changes to how hard we pull, we can have 1, 2, 3, or more nodes. And I think that is a very interesting experience for whoever do it, not for you that observe it, but for me or for the students. So for example, here I have one node, and if I let it loose, I can have 2 or 3. It's quite difficult. It's very even how to put it, micrometric changes on how hard we pull. I'm not sure if you can observe it in the camera. So this is the idea. First, to show to the students how the tension changes the speed and the wavelength, and how small changes on the tension can produce different standing waves. I was fast, I hope.
Yeah, that was really good, Takis. Thank you. Are there any questions for Takis? I know I liked this demonstration a lot. And it doesn't look like there's any questions, so we'll turn things over to Gordana in Serbia. Gordana, it's great to have you back. Thank you again for joining us. And Gordana, you're mute. You'll need to unmute yourself. Okay, there we can hear you.
Okay. Now I have one very simply demonstration. It's very good for very small kids. But here I have my Sophia, my daughter. She's going to be my school student. Okay. Video.
Well, here we have a triangle. So we can use shoelaces to do this. So we'll just take out the shoelace and this. And then we can measure it with a ruler. And then we'll get a certain number. And as we can see here, for example, that's one of the numbers. And if we take a string, we can actually see that this is the longest side, and it can go 3 times here. So it will create a perfect round. Because a perimeter over a circle is approximately 3 times the longest side of the triangle.
We have very bad technique for this. Is it okay, Michael?
Yeah, beautiful, and it's a great lead into the Pi Day theme, and to plug for next month as well. That's excellent, and it's great to see Sophia again.
Yes. Thank you, Michael.
And for those of you who haven't seen Gordana's YouTube channel, there's a number of great videos that she made with Sophia, or that one or the other of them made, especially during the lockdown, I guess a year or two ago now.
Yes. I think it's a good activity for the beginning of the lessons. What do you think, Michael? It's just sports shoes lenses. How do you call it?
Shoelaces, yeah. So most students should have them on them. You don't even need any extra equipment.
Okay. Thank you, Michael.
Excellent. Thanks, Gordana. And any questions for her before we move on? Excellent. And I've gotten a little confused in the order. While I sort things out, I think Astrinos, you're supposed to be the next after Gordana. Are you okay to go up next?
Yes.
Perfect. So turning over to Astrinos in Crete. It's great to have you back again. Thank you again, Astrinos.
Thank you for having me again. And well, my experiment is very simple. I won't need more than a couple of minutes, I think. But let me try to turn my camera. I have an inclined plane and just a cylinder. The experiment is about, well, everybody knows that the cylinder can roll down, but the question is if it can roll up as well. This is just I think it was a tomato soup can with 2 plastic cups. So I'm using this plane, and of course you will all know that something strange is happening with this cylinder. So when I leave it like here, I think that it would be an excellent experiment for Pi Day as well, and I will explain
definitely
why. So when I leave it like here, it goes up, and of course the reason is that I have changed the weight distribution inside the cylinder. You can use some modeling clay. I have put this came handy because well, I found it in my laboratory, just a piece of metal. So it changes. It has been aligned with this black line, and when I have this line slightly to the beginning of the inclined plane. It goes this way, and if it is a little, it goes this way. So it's just for fun. As I have told you, Michael, now I'm trying to, well, after David had shown that experiment before Christmas with the two weights and the conservation of angular momentum, and said that a small change can make a big difference. I make some presentations for schools that have mentally challenged students, and they really enjoy this type of experiments. They enjoy repeating them, repeating those themselves, and so even if you find it very simple, this is the reason is behind this is that I try to address a different audience for science. Well, that concludes. Thank you again.
That's really great, and I love the like being accessible for other people as well. That was great to see. Thank you, Astrinos. Any questions for him before we move on to Marco in Germany? Excellent. Thank you again, Astrinos, and Marco. We'll move on to you.
Yeah. Hi, everybody. So what I'm going to show you this time is my self-made Michelson interferometer. And I was thinking about how to bring this into my lessons. And I think doing Michelson interferometry with light is always difficult because you can't see the light waves. So I want to get the students a bit of a feeling about waves and their behavior. And I have to change my camera and move a bit around so I can let you see what I was talking about. Yeah, it looks fine. So this is as easy as it can be. So I have a wooden plate here and another one here and another one here, but this one can be moved in all directions. And in the center, I have a thin board, and I drilled, well, not my best work, some holes about 4 millimeters of diameter inside. So what I can do with this, I can take a sound source, which will be my smartphone and a sound generator to this place. And of course, I will create a sound, and the sound wave will go this way and will hit this wooden plate. And of course, this is something like a splitter. So about half of the wave goes this way, and the other half is going to travel to this way. And of course, like this, we have reflection here at the wooden board. So it comes back like so. And this wave comes back as well. And of course, we have reflection again here. So the wave is reunited again. And now I need something to detect the light, not the light, the sound. And yeah, we read it was a low-cost experiment. Well, yeah, this was, of course, but I need a smartphone and a tablet. And this may be a bit more expensive, but I'm sure you all have these devices. So I just try to switch them on and show you the next step. So on my tablet, I open the app Firefox, and on Firefox, there's a frequency spectrum app. So if I start this one, of course, it recognizes all frequencies we hear. And if I start my frequency generator on my smartphone, give me a second, I can create a sound. I just chose 1500 hertz. So it might hurt a bit in your ears now. And I don't know if you can hear the sound, but you can see here. So what happens now, I can move this board, and we have to look at this peak here, because this is the 1500 hertz detected. And if I go closer to the mirror in the center, of course, the peak goes lower. And if I move away, it goes higher. And if I even move further, it's getting lower again. So we can calculate the wavelength of the sound we use. And this is what I just wanted to show you. This is a quick demonstration of my Michelson interferometer with using sound.
That's excellent. Thank you, Marco. I know I have a couple of questions because I really like it, but I'm trying to get my head around so that the peak happens from interference between the two reflected waves, like the one that was reflected at 45 degrees and the one that was transmitted. When the fan is blowing, that should affect the wave speed in one direction, but not the other. Does that shift where the peak is, or just the magnitude of the peak?
Only the magnitude.
Okay, because there's weaker interference.
Yeah.
Is that the correct interpretation?
I think so, yeah. And so we change the speed of the sound, but I don't think we change the wavelength here. I must recalculate this again, but we only can see a moving in the magnitude here, yeah.
Okay, perfect. I think it makes sense. I'll let you know if I have trouble setting it up once I try and do it myself. Any other questions for Marco? And I think next we should have Caroline Neuberg in England. Caroline, are you ready for us to turn over to you next?
I am indeed.
Excellent. Thank you for joining us. And this is the first one that you're presenting at, so I'm especially eager to see what you have for us today with your density bottle.
Thank you. Well, hello, everybody from a stormy weather in the UK. I have a very simple experiment and I have a little PowerPoint to show you, but I will just start with a plastic bottle. If you can see, plastic bottle with a clear liquid inside. And inside this here, I've got two types of particles, the yellow one and the pink one. The yellow one are called poly beads. So I'm going to show you in a minute what it looks like in a present. There are just some little plastic beads. And on the top, the pink ones are beads that you use and then you iron them and then they form a solid block basically. So they're a little bit special, but they're all plastic. And what I love with this experiment is that in this supposedly one clear liquid, those beads are just located right in the center. But actually, I know that as you are all science teachers, that it's basically two liquids here. But the beauty of this is if I give it a good shake, and it's shaken, not stirred, a nice good shake, you will see that the yellow one falls to the bottom and the pink one floats to the top. And we've got one liquid, and that would be the end of the experiment. But if you just wait, and just wait a bit more, and just wait a little bit more, then the beads get back together. So if I can share my screen with you.
Yeah, go ahead. That'd be great.
Yeah, back where we are. So I've just started or just designed a very small presentation. Let me see. Can you see my screen?
Yes, now we can see it. Well, I can at least. If anyone can't, let us know. But yeah, it's coming through well.
Okay, so basically to design this, you need a plastic bottle, you need to wash it with distilled water. Then you're going to use actually two liquids. You're going to have isopropyl alcohol, so-called rubbing alcohol in English. And you're going to use the same volume of this alcohol as the volume of the distilled water you are then going to mix it with. But that distilled water, before you mix it together, you're going to mix it with a 25% concentration of just salt, sodium chloride. And then the pony beads are those kind of beads here used in jewelry. So if you have a sort of arty kind of place, they will have those kind of beads. And then the perler, the one that have, sorry, that's bad planning on my side. Those perlers are the pink one here. They are the ones that you use, and then you see you iron them and form a little design or so. Now, what you have then is basically the isopropyl alcohol will be at the top, it's lighter one. Then you have a range of density, the density of the perlers, then the density of the pony beads, and then the salt solution at the bottom. But when you mix them up, you have miscibility between the alcohol and the water, but due to the presence of the sodium and chloride ions, you are going to then segregate the water from the alcohol. It's called a salting technique, basically. It's one of those techniques there, and they are immiscible, and so you get those beads to get together. And this is the experiment that is continuously on my desk at school, and students absolutely love playing with it. So that's my experiment for you for tonight. Thank you.
That's beautiful. Thank you. I know I've seen a density bottle with the poly beads before, but I hadn't seen it with the salting out technique. So that's definitely a new one I'm eager to try. Another cool one to mention with salting out, if people aren't familiar with it, is you can have a 3-level density column, where normally if you have a density column and you shake it, you'll just get the hydrophilic and the hydrophobic layers, and you'll only get down to 2 layers. Whereas if you have isopropyl alcohol, and I'm sure there's other solvents that could work for that too, and you have a concentrated salt solution, then it'll salt out the alcohol. So you'll be able to get 3 layers, even if you shake it up, and it'll separate. So that's not what I'm sharing today, but that's something that it reminded me of, to share an additional idea for that. Does anyone have any questions for Caroline before we go on to Iuliana in Romania?
I think that's a very good one to get the students to actually explain, because you've got the 1, 2, 3, 4, 5 different densities in the whole experiment, and just get in a mix-up. Actually, I'm sure the teachers can get in a mix-up, but just explaining this is the most dense, then this. When we mix them, this happens. It's a really good exercise to get them to either explain verbally or written down just what's happening, because it's quite easy to understand what is actually happening with the different densities, but to actually go through all the stages is quite a difficult task for students, and it can be any age more or less can do it.
Absolutely, and I think everybody coming in my classroom just love playing with that bottle and just seeing them all together. So thank you. Thanks, David.
And anything else before we move on to Iuliana in Romania?
Good evening. Good evening. My experiment tonight is about polarization, and as you know, there are very cheap 3D glasses for cinema, so I use the filters to bring this experiment at my classes. Just a moment to move. Yes. This is my stand. I've mounted these filters on like a holder with stem, and I can I can rotate the filters, and as you can see, light goes off and on. And we can demonstrate light is the transversal, that light is a transverse wave. Of course, if we mount a third filter, but not only, we can, just a moment, to shut the light off. Yes. And this is another provocation, because you can ask your students what happens if we bring the third filter in between. And of course, they have many ideas, but they don't expect that actually they can see what is behind the screen. This is quite spectacular for them. They don't expect, because we explain to them that the wave can pass through the one direction, that usually the electric field is in all direction, and this is what these filters do. And of course, the next experiment would be to bring a plastic that was stressed before, like this, like a clear plastic, and they can see these interference fringes. And another application is that is used in industry to test the stress of materials. And this can be after making arts school, because if they stick clear tape on some plastic, they can see those nice colors, and actually can do some light paintings. I have actually I have not an artistic I'm not an artistic person, but some of them are really talented, and they've done some interesting paintings. And I would like, this is not something that we can do with a household, but I have bought like a crystal, like Island spot, calcite, you know, calcite, Island spar. This is an isotropic material. I can demonstrate what happens if we see these two, these two lines, and if we rotate, you see ordinary and extraordinary rays, because it's an anisotropical crystal. And what is interesting is that those rays are perpendicularly polarized. So if I rotate this, you can see one and after the other. So it's very interesting, because I can explore the methods of obtaining polarized light. And of course, I won't turn my camera, but maybe I will, to the screen. Sorry. I hope I will do. Just a moment. There are too many things. You see, I don't know what I cannot see what you can see, but just a moment.
So we can see about half the screen. We'd see it slightly better if you're able to shift it even more to the right, I guess.
Like this, just a moment. Can you see something?
There it's coming through well on the side of the screen, yes.
Yes, because I cannot. So these Scotch transparent plates introduce some shift in the phase of different colors. So interference is dominant for a color or another. I don't know. You can see this. Okay. This was my experiment for today.
No, that's excellent. Those are really nice demonstrations of polarized light. Does anyone have any feedback or questions?
I'd like to jump in there, Michael. Yeah, thanks, Iuliana. That's really good. I love the way that you use the lenses from the 3D.
The stems, yes.
Yeah.
And actually, I can rotate very easily.
That's brilliant. That's brilliant. And it works really well if the students are at home and you have to remote teach. It looked really well, so they could maybe make as well themselves.
And they are amazed when they see so many colors. It's a little bit difficult to reproduce what they really see because the screen, the surface of these filters are rather small.
Okay. And the last thing I want to say is that is a very nice piece of calcite. I wish I had.
Yes, actually I have bought with only about 10 euros. 10 euros in Romania from online. I have 4 pieces, and I also have some TV TV stone.
TV rock, yeah.
TV rock. Yes, thank you.
You must send us the address so that
yes,
we can buy.
Yes, the universe of crystals from Romania. Really.
Thank you.
Thank you.
Beautiful. Anything else for her before we move on to another experiment?
Michael, may I say something?
Yeah, of course. The master of polarized light, of course. I was expecting you to have something to say.
No, I'm not. Thank you very much for the experiment. I like to put vision glasses between the polarizers, and we can see
in a mirror.
Excuse me?
Mirror, to look in a mirror.
No, to put the glasses between the two polarizers, and we can see where the frame of the glass stresses the glass.
Yes.
It's very interesting.
Yes, but it's another experiment that you, when you look with your glasses in a mirror, it is something very special. So just try it.
Yes,
you can see one eye, and the other you cannot see. Use the mirror. Thank you.
Thank you.
Excellent. And anything else on polarized light?
You can use this cassette finding the sun on a very cloudy day, and it said Vikings use this for navigation. So
yes,
great activity for students if you have a lot of these cassettes.
I have done this. I tried, and indeed, I'm not sure that it works. Really, I don't know. I know that that sky emits polarized light, but and indeed, I made something like this. I was rotating, and where the two images of a point were overlapping was like. But I couldn't figure out where the sun is.
Excellent. Any other ideas with polarized light before we move on? And moving on, we're actually going to skip back in the original order. We had 1 or 2 latecomers, and I'm still wondering, did Violetta from North Macedonia end up showing up? I don't think so, but we have Jeane de Fatima from Brazil, and some of you guys might be familiar already. She's not very confident with her English, so she's getting me to read another text, and then we'll see a short video from her. So the background of this one is there's a student who's in Canada, who a lot of you know that's actually where I'm from. So her student, Anna, in Canada is freezing bubbles. And so it's actually along the same lines as David's one on bubbles, but this is a freezing bubbles one. So just the story behind this one. Anna, a Brazilian student who lives in Canada, participates in Zoom classes with classmates. In Brazil live every week, and they do experiments together. And one of the experiments she did with her friends back in Brazil was looking at snow and everyone sharing the temperature in real time. And she did an experiment to see what happens if you try and freeze a bubble at minus 18 degrees. So someone braving minus 18 degrees with their bare hands to show the effects of a freezing bubble. Let me know if the image and the sound doesn't come through clearly when we're doing this. And here we go. And Jeanne de Fatima, you are with us. Do you have anything you want to add, or did we okay, and the same text anyone that I was reading from with more details on the names that I kind of skipped over because I couldn't see it small, so we have that in the chat as well. Does anyone have any questions or feedback on the freezing bubble before we move on to David with bubbles that aren't frozen in England?
I'd just like to mention you've beaten me to it, because my what happens next on Monday and Tuesday next week is freezing bubbles, and I've got some fantastic videos from Slovakia, from Lucia Dovalova, of bubbles freezing, which she's done in a freezer as well as outside in the cold, because I felt it was a bit unfair that we didn't have -18 to do it. But maybe a good thing that we didn't have -18. So what's next? What happens next Monday and Tuesday? Right.
So I don't know if it's a good thing or a bad thing that we might have spoiled part of the surprise for that. But I'm sure. I know I'm looking forward to checking it out, and I hope everyone else checks out your videos on what happens next as well. So we'll shift over to you. Do you want me to play your video, and do you want
I'll just do a little introduction first.
Perfect.
One of the things that really I think is good is to use things that the children already have. And of course, most children have a little bottle like this with which they blow their bubbles in, and they love playing with them at any age. You give them one of these. Now that was all I had when I was a little boy, but of course nowadays there's all sorts of wands you can get, and different size wands and so on. I can even send a stream of bubbles over from a machine, which is really great to do those things. I'll just switch cameras and show you downstairs here, if I do it very quickly. There we go. The other thing which I think is really cool to do with bubbles is to join them. If you blow bubbles on a plate, you don't blow round bubbles, you blow hemispherical. You don't blow spherical bubbles, you blow a hemispherical one, which if you're at an advanced level, you can do the sums and work out the different pressures, because there's the surface tension of the bubble, there's the pressure inside, the amount of air inside, and the curvature of the bubble. Make a half one like that. So it's a hemispherical bubble. Join another one to it. And of course, you get a straight line join, which of course tells you that the pressure in both bubbles, both halves, is the same. If you have a smaller bubble, the pressure inside the smaller bubble is greater. So you can get a curvature. If I can show the picture there. And of course, you can also join bubbles together. The smaller bubbles up. Oh, sorry, that's still straight. That's still straight. But I've got another one where if you have a small bubble onto a big bubble, the smaller bubble pushes into the big bubble. So you don't get nice straight lines. And of course, you've got the geometry there as well with the hexagon in the middle. So it's a good job I didn't try this live because it's blowing a gale outside. The video, if you play that now, I did outside when it was a calm day, just in case. So if we skip to the video.
Well, if you look carefully, you might have guessed that we're playing bubbles this afternoon. Bubbles, wonderful, wonderful things. Just switch that one off. And some little questions with bubbles for you today. So just lower the camera. And the first thing is, what about the size of bubbles? So I can make these bubbles small, lots of little ones, or if I blow harder, I get small ones, but gently I can make bigger ones. So how is it that you make big ones when you blow gently, and smaller ones when you blow soft. Pressure in a small one is much bigger. It's about the bubble detaching and so on. You can look into that. The other thing which is fascinating about bubbles is that they all seem to turn out round. So if you have a frame like this with these oblongy shapes on for the frame, and we make some bubbles, they all turn out round. If you look at that in slow motion, you see that they sort of don't start round, but they move to be round. So the bubbles, the best shape for them is round, and you can work out why that is so. Of course, you can see that the kids have these things as well. If I open it the right way around, it won't spill. But that's not going to produce a round bubble. Well, yes, it does. You can see how they appear and then they come round, and if you're careful, you can catch one like that and examine it a bit more. There you go. So bubbles become round, except there's an exception. If you blow a bubble, if you see a bubble on a road or somewhere, look at these bubbles. They're not perfectly spherical, they're hemispherical. Why is that? So why do you get these hemispherical bubbles? Well, I've got this, I'll bring it up to the camera so you can see. If I blow one nice bubble, they're bubbling a bit. One big one there before it bursts, you can see the bubbles are joining together, and they join in very mathematical patterns. I'll show you some pictures of those later perhaps. But the point is they're all hemispherical. And in fact, that's a much more stable state than the round bubble. There's less energy in the hemispherical bubble. And last but not least, this is a lovely bubble wand to create a long bubble. I said they will form into spheres, but in fact, this has little areas so it can hold a lot of bubble mixture. So when you produce a long bubble, it then breaks up and again forms into the spherical shape. Get enough bubble mixture on. Oops, it's a bit windy. You see that? Oh, there's a good one. But when they break up, again it moves into spherical shapes. Wow, that's great. I like that. I'm glad I bought that one. So there's a few little ideas about bubbles that you can take. I mean, they can look at the colours of bubbles. When you get these a lot of bubbles, if you look again at them, you can see how many colours you can get. You can look at the colours. You can look at the reflections in bubbles. You can look at the stability of bubbles. You can look at the mathematics of bubbles, the pressure because of the different curved surfaces and so on. Ooh, that's rather clever, the way they've clung onto that. I've never seen that before. Anyway, enjoy playing with bubbles.
So that was just a sort of introduction to bubbles, really. The more you think about it, the more things you can do in terms of the science of the bubbles. You can you've got the formation, the pressure, the surface tension. You can look at interference patterns on the bubble. You can actually look at different bubbles, different sizes of bubbles, and the different images in the bubbles, because you've really got little convex mirrors with different curvatures. and so on and so forth. So just hope you like that introduction. And as I said, I keep discovering new things to do with bubbles, and there's some fantastic toys with bubble helicopters and bubble you-know-whats that the children can have now. And there's a little bit of science in them all. So that to me is a lovely way to get into the science. Is if they've got these toys at home, you can talk about the physics of them as well. Okay, that's me done.
That's beautiful. Thank you. And I'm always amazed at the amount of science there is behind bubbles as well. Like I've been at a university discussing with a postgrad student in mathematics, looking at how he was using bubbles to study minimum surface area problems.
Yeah.
Because a bubble will always tend to minimum surface area, which is, of course, why you get the hemispheres, the spheres, the 120-degree angles. But you can get really complicated forms. Like he'd make hypercubes out of it.
Yes. I mean, that's another area where you use the soap films and have straws and squares and so on, and you can get a little cube in the middle. All sorts of things people do. But it's just, I think it's a very good subject for a science club to get involved with, because they can start making these different shapes and so on. And it's interesting. I like to get the children interested in some aspect of physics, and then they can develop it themselves, and then they come out with something that you didn't know, which is always a good sign.
And another surprising thing to do with bubbles too is looking at the shadow of bubbles, and it's a bit tricky playing with the light in the right way for that.
Not doing that.
But you'll have seen, well, you mentioned the interference pattern you see from bubbles, but you can get a negative version of that. And so if you do it just right, you can get it significantly brighter and have really bright, beautiful bubble shadows that show interference.
The bubbles that I had, the semicircular bubbles that I had in the freezer, produced a lovely set of like Newton's rings type of interference bands as they gradually got colder. But it was very, in the freezer, it's very critical. They sort of get so cold and pop, and that's it. But as I say, I've got some lovely videos coming up. You'll see those later.
I'm looking forward to checking them out. Does anyone have anything else to add about bubbles before we go over to Paul in Ireland?
Can I just ask a novice question?
Questions are always great, yeah.
So I just don't understand. So the smaller bubbles have a higher pressure. Is this correct?
Yes. Because, I mean, well, there's always a because, but because the curvature is greater. So if you think of the tension in the bubble film, and you have a smaller angle, then there's more forces into the middle. Whereas if it gets bigger and bigger and bigger, there's less pressure into the middle. So you've got to be careful if you sort of try doing anything with boils or anything like that, because when you're blowing a big bubble, you're putting more and more air in. It's not the constant mass. I think we're going to get a balloon demonstration here of the high pressure in the small balloon. Michael's going to show you this. I love this experiment. I was very pleased that when my son was at Oxford, he got this wrong when I asked him which one will happen, which one will blow the other one up.
and if you drop it, it doesn't work at all. But yeah, the smaller bubble reminded me of the same effect, and perhaps you'll agree, like this can demonstrate the same principle why the smaller bubble is higher pressure.
It is, except that the tension in the bubble material is much greater in the small bubble.
So that has to do with the elasticity of the surface.
Yeah. If you plot the pressure in a balloon as it's blown up, it starts high,
yeah,
and then goes low. And the beauty of this experiment is that little children can understand it because you say, when is it hardest to blow the balloon up?
Exactly.
When do you have to ask mummy to blow the, you say, will you start the balloon for me if they blow balloons up? And then they realize once it's started, it gets easier. So once it's started, the pressure goes down until the very last moment. Because if you have some clever so-and-so who knows about this experiment, if you blow the big balloon up to just before it bursts, the pressure goes up again. So you can get the big one to blow the little one up. A little bit anyway.
And I'm not actually 100% confident this will work because it works much better if you use two brand new balloons that are the same. And these I just pulled out of a bag of stuff I had while traveling recently, and these have blown up several times. So I'm not sure it'll be a good demo.
No.
But should we get everyone to predict, like from the discussions we just had? We should have led to it. But everyone throw a prediction in the chat if you think the small one will give air to the big one or big to the small. So put S if you think small will empty its air out, B if you think big will empty its air out. In 3, 2, 1.
Nothing happened.
Yay!
So it wasn't a huge effect, but the small did empty into the big, right?
Just give it a squeeze. It's fine.
Yeah. No, it definitely is good to use newish balloons for that, if not brand new balloons that are exactly the same. But that was one of the ones you showed last time, David. Except cheaper, I tend to just have a single tube, but the Y would make it easier and less likely to drop it the first time I try and demo it. Anything else before we switch over to Paul in Ireland? Excellent, Paul. I'm looking forward to seeing more magic of science.
Great, yeah. Can you hear me?
Yeah, loud and clear.
Great. They're fantastic, and I'm reminded of the curiosity, and I think bubbles just bring us back to when we were about that high, or in the cradle, and you can make really nice bubbles with pieces of rope and wands and really big ones. Okay, so I'm going to show you another little bit of magic. Apologies if you have seen it before, but I'm hoping that I will show you something maybe that you haven't seen. So what I've got here, and I have to move back a little bit, but I'll show you up close, okay, is I've got this bathroom chain, okay? So you might have a plug on the end of it, or you can use a fine chain that might go around your neck, but I don't have one of those. I do have a bathroom, and there was a plug on this, but no longer, okay? And this is called the chain and ring experiment. I'm trying to get all of me into the camera. Okay, so the ring sits through the chain. And the question that you could ask your students is, what happens when we drop the ring? Okay, so here we go. 3, 2, 1. Oh, it didn't. It didn't fall straight through. Okay. I once saw a giant machine automated do this in Barcelona once. So machines can actually reproduce this, but I'm going to show you how this one works. When you drop it, you just ever so slightly release it at the front first, and then the ring rotates and catches on the bottom. Okay, now there's different ways that you can do this, so it does need a little bit of practice, but let's try it again. Okay, so you're not going to see it, it's ever so slight. If you think too much about it, actually it doesn't work. Okay, but what has to happen is I'm going to release it at the front. I'm going to keep my thumb on the back, and that's going to cause a rotation. Okay, so 3, 2, 1. Oh, didn't work. Okay. But as I said, it needs practice. We need that rotation. Okay. I'm going to show you something else that you can do with the same piece of chain. It's called the one-hand knot. Okay. So I don't know why you might want to have a one-hand knot. This is the one-hand knot. So to make the one-hand knot, the thumb goes around the chain. It goes round the back of the other. And then we have a scissor action, which will catch the knot. Now, this is, I hope you can see on the camera, this is a very special knot because it will move up and it will move down according to how I pull the chain at the top. Okay. So you can hopefully see the knot is going close to the bottom. And the question is, what will happen when the knot reaches the bottom? Okay, we're nearly there. Nearly there. Well, the knot comes right off. You want to see the knot again? Okay. The thumb comes around the back, round the other one. You reach down, you grasp, scissor action, and here's the knot again. Make it lower. Watching carefully now. This time it vanished altogether. I'll leave you that one to think about. Michael, have we time for another couple more?
Yeah, let's go for one or two more.
Okay, all right. This is a little bit more magic. It's called the elastic elevator. And I could use the ring, but what I'm going to use is, it might be more visible. This is a paper clip. Now you could use a ring for your finger, or the ring that dropped on the chain. So what I've got is, I've got the paper clip on the elastic, and I assure you I am keeping my fingers, the distance between my fingers, quite still. But what we should see slowly happening is that the paper clip should start to rise up the elastic band. Now I'm doing it quite slowly, so you mightn't see it, but hopefully you can see that it has moved a little bit. What I'll do is I'll get it to move a little bit quicker. So it's the elastic elevator. Okay, I hope you saw that, but the question is, how is it done? Okay, there's no magnets. It's not telekinesis. I'm not moving it with the thought of my brain. There isn't static electricity going on, okay? I will reveal to you so that you can amaze your students and others how it actually works. So what you do is you take more elastic than what you need down in this hand, okay? And very, very slowly and slightly, I'm letting the elastic slip between my fingers. So the paper clip is not actually moving. It is the elastic band that's moving, but it gives the impression that the paper clip is moving on the elastic band. Now you may say, where's the science in that? But let me tell you, I have got a complete 40-minute lesson out of that equipment, because you can draw force diagrams, free body diagrams. You can talk about elasticity. You can talk about friction. You can ask some really nice questions. Can the elastic band go all the way to the top? If it can't go all the way to the top, how far will it go? Well, it will go what's in this part here. If it doesn't go all the way to the top, what stops it? Is there an optimum angle that you can that you have to have? There's a whole lot of physics on there. I'm going to leave it at that because we're just after 5, but I do want to see Michael's experiments before we leave. So thank you, everybody, and thanks, Michael, for putting this all together. It's really enjoyable. Thanks.
Oh, thank you, Paul. It was great to see more magic. I'm looking forward to seeing even more in the future. So moving on to my
Can I just put in there?
Oh, yeah, of course. Yeah, go ahead.
For me, the best lesson from the paperclip and elastic is that if you ask the wrong question, you'll never get the right answer. Because what most people say is, how is the paperclip moving? Whereas the question is, the elastic band is moving. So if you ask the wrong question, you get the wrong answer. You never get the right answer. And I think that's a sort of life lesson almost in that. Sorry to butt in. Yeah.
No, that's great. Does anyone have anything else to add before I finish up with my experiment? And so finishing up with my experiment is actually an experiment in and of itself, how I'll be doing it today. And I'm going to explain that. So I'm going to attempt to do my experiment in silence. And I want your feedback from it on how well it goes. The reason for this is because roughly 2/3 of the people attending these meetings are non-native English speakers. And of the people presenting, there's been roughly half of them who at some point or another have expressed nervousness or delayed presenting because they weren't confident speaking in English. And so I'm always looking for ways to try and encourage more people to participate or to be more inclusive. So one of the ideas that I actually got from one of the participants, a lot of you guys might not have noticed, in November's experiment share, one of the presentations actually had no spoken words. And it went so well that it was only when I pointed it out to people afterwards, they noticed that. So I'm going to go through a fairly simple experiment, and it's one of my favorite ones, so I'm sorry if some of you might have seen it before, but I'm very interested in your feedback afterwards, whether or not it made sense, and whether it's worth trying to have one experiment share 1 month where we only have silent experiments from everyone. Because that'd be a difficult thing for people who are used to speaking to do, but hopefully to be a little bit more inclusive. So to not leave you in complete silence while I'm not talking, I'm going to put on some background music. Hopefully the music's coming through. Okay, now I'm back to talking again. And I don't think well, I was disappointed with how the experiment itself went. I tried it right before starting and things were charging up better than they were live. But that's kind of how things go. But that was my attempt at doing a silent triboelectric series charging different objects. And I'm really interested in feedback people might have on whether or not it would be a good idea to encourage more silent experiments or to do a whole silent experiment share one time. So if you have ideas on that, please let me know. I've also created a short poll for the, like, rather than one by one, everyone's saying what they think. In addition, in the poll, I have the idea of maybe having an Earth Day themed experiment share in April, but I think a lot of people joining these aren't all that interested in Earth-themed experiments, so I'm interested in your feedback on those too. So here's a poll. If you have feedback that fits into the poll, please answer the poll, but also if you have anything you want to jump on your mic and feedback on that, please let me know. And I'll give I don't know, however much time people seem to need. There's a couple of results coming in. I'll give like 30 more seconds for the poll, and then I'll share it with everyone. But if anyone has anything they'd like to feedback verbally as well, let me know.
Michael, can I say something? I thought you were great, as you always are. When the experiment didn't go the way you wanted, I'd say that's when you really wanted to speak. Would I be correct then?
Yeah, it was really hard not to apologize and say, like, sorry that this isn't how it's supposed to be going.
Yeah, but I think as a concept, to include everybody, I think that the mime is great. It takes a lot of work. You obviously thought about it. I am always amazed when people present in a language which is not their own. I was once asked, how come my English was so good? And it's my only language. So sometimes I feel inadequate, and I'm humbled when other people can present in another language. But I think sometimes we don't need the language. We can see what's going on, and the science breaks through the language barriers.
Thank you. I feel just the same way. And like on the note of presenting in other languages, just over the weekend, I was down in Spain for a memorial for a teacher, and it was really a beautiful way to remember someone's life with a science fair and with people sharing experiments. And I haven't been back to, like, I hadn't been to Spain since before the pandemic, so my Spanish was absolutely awful. And I forgot how awkward it can be trying to present experiments in a language that you're not all that comfortable with. But also, like, another thing to add from that is that one of the things I've noticed over the years is there's different experiments that pop up in different countries. And until someone translates them or brings them to another country, they don't always jump across a barrier as well. And so if we can find ways that we can include more people who aren't necessarily comfortable in English, then we can have a lot more experiments that we can have access to. So I'm quite encouraged by people's feelings in the polls. There were even 7 of you who said you'd love to present in a silent one. So I'd say from that, then let's do it. We'll have a silent experiment share coming up. Perhaps for May, either April or May, depending on whether or not I go ahead with an Earth Day one. The March one coming up, that'll be March 13th. It's Pi Day Eve. So as I announced before, we'll have a Pi Day one. But I bumped it back to the weekend for 2 reasons. One, there were a couple of you who asked, can we go back to having one on a weekend sometime, because weeknights aren't good for everyone. So for that reason, but also last year I actually celebrated Pi Day Eve as well. And one of the reasons for that was to share ideas before Pi Day that people could do on Pi Day itself, rather than just to celebrate for ourselves, because one of my biggest goals with these experiment shares is hopefully a number of you are bringing these experiments to life in your classroom and not just doing it for your own entertainment. So those are those things coming up. I just have 1 or 2 more announcements I wanted to mention as well. A number of you have already joined me for my Particle Physics for Kids virtual camps. If anyone's interested in that, please invite your students along, come join yourself. If you have something in particle physics to share, I haven't set a date yet, but I'm really looking forward to having Marco back on for his bubble chamber one. It was what actually taught me, like, where I got comfortable understanding what detectors do for the most part. So I love being able to share that with other people as well. If anyone has any contacts for particle physics that I could ask to have on, please let me know. 2 other things I've mentioned, Yes International, a lot of times, which is the student version of these experiment shares. One new thing with that I haven't been doing before, I'm going to start having open sessions. So it'll work just like the experiment shares, only it's students sharing experiments with each other. So students from any school anywhere in the world can sign up to share experiments to other students. Up until now, it's just been like whole clubs of schools who are ready to present a whole session of experiments at once. And it's been a nightmare to program, and a lot of schools haven't really felt ready to have more than 1 experiment at a time. So hopefully that'll open things up and include more people. If you have students who'd love to, or who'd like to share experiments or just watch other ones, let me know, and anyone's always welcome on those, including 2 special ones coming up. I'm going to Ghana in 2 days for 2 weeks, and one of the experiment shares, one of the Yes International meetings will be at Ho International School, who's one of the founding schools of it. They've done a whole bunch of sustainable development projects they're eager to share with other students. So everyone on my Yes International network, and anyone else who wants to join in, they'll have like a probably 2 or 3 hour session on that. And there's also, if there's student interest, going to be an open one for other students interested in presenting experiments while I'm down there. Final announcement, because this is dragging on, and I thank everyone for their patience staying with me this long. I've already spoken with a couple of you who are willing to share some experiments via Zoom while I'm down there as well. Astrinos had the great idea of putting together a magic show. And so I've asked a couple of you if you'd be interested in doing some magic experiments. I know Paul was the first one I asked, and you seem to be up for it as well. Anyone else who wants to join on for that, the more the merrier always. So let me know if you have any ideas for that. I think I've kept everyone long with announcements, so I'll stop talking now. But anyone who wants to discuss any of those ideas further, I'll keep the Zoom session open if anyone wants to hang around for a couple more minutes. but as it's already getting late, I want to thank everyone again, both for attending and sharing these experiments, and especially everyone who presented experiments. So thank you again, everyone, and have a great night.